In this session, we will be discussing how Auger-Meitner peaks arise and how we categorize them. You may have heard of the term Auger peaks before. This is the same thing, though in recent years a shift towards the use of the term Auger-Meitner to recognize the simultaneous works of Lise Meitner alongside Pierre Auger has taken place. Now, these can be recognized easily on an XPS spectrum. They are large, they are broad, and they often contain a lot of structure, unlike the concise and sharp peaks from photoemission processes. One key attribute of Auger peaks is that if you analyze them with a different energy source, so here we have data from a magnesium K-alpha X-ray source, and now add data from an aluminium K-alpha X-ray source, we observe these Auger peaks appear to shift in binding energy. Now in reality, what we are observing are peaks with a fixed kinetic energy. So if we now plot this with kinetic energy on the x-axis, we see the Auger-Meitner peaks overlapping and the photoemission peaks moving in kinetic energy. Now this makes sense because our photoemission equation tells us that the kinetic energy of a photoelectron is equal to the photon energy minus the binding energy. So as we increase our photon energy, we increase the outgoing photoelectron's kinetic energy. We do not, however, increase the kinetic energy of this Auger-Meitner peak. So what's going on here? The reason for this comes down to the Auger-Meitner process itself. When we excite a photoelectron, we leave behind a core hole, an electronic vacancy where our electron used to be. But atoms don't like being in a state like this because it's no longer the lowest possible energy state. So it relaxes an electron from a higher energy orbital, typically in the valence state, and fills this core hole. But in doing so, the electron must lose some energy because it's now in a lower energy level. And it can do so in one of two ways. One is to emit it as radiation, a process known as fluorescence, which tends to be the predominant mechanism for heavier elements. The other way is to send this energy to a neighboring electron and release the energy in the form of kinetic energy as a newly freed photoelectron, but a special type of photoelectron, an Auger-Meitner electron. Because in this case, the photon energy in our photoemission process is equal to the energy lost by the relaxing electron. This is always fixed. It doesn't matter what source energy you use to create the initial core hole, the energy gained from relaxation remains constant, and so our outgoing Auger-Meitner kinetic energy is also a constant. Now the naming of these peaks is a little different. We have 3 electronic states involved, and so we end up with a 3-term nomenclature. We also use X-ray notation to name these transitions, which does actually simplify the name somewhat. First, we have our core hole. So in this case, a 1s orbital or a K shell. The next term is our relaxing electron state. So in this case, a 2s or an L1 electron. And then finally, we have our outgoing Auger-Meitner electron, which here is a 2p or an L2 or L3 shell electron. And so you might start to see how we end up with these big broad ranges of peaks. The energy separation between combinations of shells, especially when we also have our initial core hole in a shell subjected to spin-orbit coupling, as we see here with nickel, means that we end up with many configurations in a similar energy range. Here we can see core holes from the L2 and L3 shells, so the 2p doublet, and relaxing electrons and Auger-Meitner emissions from the M2, 3, 4 and 5, so the 3p and 3d orbitals. Now these regions are often more sensitive to valence chemistry than photoemission peaks, but as you can see, they're not always particularly easy to work with. So we're just going to finish with a quick refresher on X-ray notation, and this table is going to be made available to download on the page below for your reference. The letter refers to the principal quantum number. N1 is K, N2 is L, N3 is M, and so on. Sometimes you might see V used as shorthand for valence shell. So for example, an LVV Auger transition, but more commonly used is the full form. The subscript number then refers to the total angular momentum state. So starting with an s orbital which has no spin-orbit splitting, we have 1. Then into our p states, 2 and 3, d, 4 and 5, and finally f, 6 and 7. And so you start to see that these X-ray terms contain a lot of information about the electronic configuration of the electron in question. These are still widely used in physics and in many spectroscopies, though for chemists and indeed in XPS in general, we tend to use chemical notation instead. So that's Auger-Meitner electrons. They are very useful for some quite advanced topics, and now you know the theory behind how they arise and how we name them.